Okay, welcome to class. Introduction to Deep Learning. We're in the middle of stochastic gradient descent. We talked about gradient descent, we talked about backpropagation, how to set up a neural network, how to compute gradients, and how to train the network, optimize the weights by what is called gradient descent, which kind of incrementally modifies the weights so as to improve the loss, to reduce the loss. And we talked about how to make this scalable because this is important, because we're not only estimating one or two parameters here, but we're estimating thousands and possibly millions of parameters, so you need to do this fast. This is not easy. And this is a numerical challenge, and one way to get scalability is by this technique of stochastic gradient descent. Sounds complicated, but it really means you have all this training data, millions of training samples possibly, right? And each contributes a gradient that tells you which direction should you change the weights, right? But rather than looking for all the samples at the same time, you take subsets of samples, so-called mini batches, and then you basically average over that mini batch and use that gradient to update. And the idea is if the gradient, if you have an unbiased sample of training samples, so a random sample, then you can assure that you get what's called an unbiased estimate of the gradient. Meaning it's not necessarily the exact gradient, but it's a stochastic approximation of the real gradient, and that should be fairly good to update the weights. And obviously, the larger your mini batch, we talked about it, the better is your gradient estimate. And so you have an interest in going for large mini batches. Ideally, take the whole training set as one mini batch, except that doesn't fit on your GPU. And so typically, the size of mini batch is determined by the memory of your GPU. And you will go for the largest possible mini batch size. And then we said then you can do mini batches, you can do stochastic gradient descent. But what you will find is, and this is very often the case, that loss functions can have a very anisotropic nature, meaning in one direction the cost will decrease a lot, like you have a very steep valley, and in another spatial direction or dimension, it will not change much. Here, the example is always parallel to the respective axes. That doesn't have to be. You can have directions which are, diagonal or something. And this is very reminiscent, very much of, hiking in a landscape, where in one dimension you would have a very wide valley, whereas in the other you might have a very steep valley. And so then the issue is that the naive gradient descent will tend to oscillate. You will do update steps that are typically the standard gradient descent updates are, orthogonal to the level lines of constant energy. So this will step here, this will step here, this will step here. And so you see, whereas in X direction we're moving towards the goal, in Y direction we're jumping back and forth. And as we said, if your step size is too large, you get oscillations. What we have here is more complicated. It is a form of oscillation, but only in some dimensions, in some directions, not in others. And so you want to adapt the step size in a way, or you want to adapt the stepping such that it can distinguish different dimensions, different directions. So that in this case, you want something that does large steps in the X direction, but small steps in the Y direction. And last time we talked about one way to do it, and that was called momentum, where you, let me go back and show you the basic idea of momentum. Where is the momentum? Here it is. So the idea is that we have this so-called velocity vector that aggregates the gradient vector over time. It's a weighted average of all the past gradients. And if you do that with a gradient that moves up and down, then in the y direction, the averaging means you reduce it. Whereas in the x direction, where you consistently go in the same direction, it will lead to an increased vector. And so the vector that vk generates is a vector that will be large in the x direction, like we wanted, and small in the y direction. And then we use that vector for updating. And then we saw this famous Yuri Nesterov came up with an even more clever way to do it. Where is this Nesterov momentum? It's practically the same, except that he computes the gradient not in the past, but kind of forward-looking. And that gives you an even faster convergence, and he actually proved that this approach gives you a very good convergence rate. And Yuri has a lot of papers on optimal convergence rate, showing that among all conceivable gradient-based approaches, his approaches give you the best possible convergence rate. And that is, I find, quite impressive results in terms of the technical innovation. And so, not surprisingly, Nesterov is one of the most famous people in this game of optimization. He worked both on first but also on so-called second-order methods, Newton methods. We'll talk about that in a bit. Now we come to an alternative way to do this adaptive that has a similar effect and is kind of complementary, a technique that is called root mean squared propagation, or RMSprop. And it's a little bit similar. The idea is to how the aim is to also reduce the oscillation in the dimension, in the direction where, you know, the loss function changes a lot. And so the idea is similar, and in fact what we are creating and computing in this variable s is not the first momentum, but it's an aggregation, or it's what's called the second momentum. It's essentially the variance of the gradient, right? So what you have here is this dot product. It's an element-wise multiplication. That's important. The gradient, as you know, is a vector, right? If you multiply two vectors, we're not doing the dot product of the two vectors. That would give you a scalar. No, we want a vector-valued output. And what we do is we basically multiply these gradient vectors component-wise. So the first component consists of, you know, the first component of the gradient squared, the second component of the gradient squared, etc. So that is your vector. It's all the squared derivatives as a vector. And what we want is if those are large over time, so the variance is very high, then we basically divide by this, right? And so this creates what you could call a variance normalization. So you have the gradient vector, it has lots of components, and they're normalized based on their variance such that the outcoming vector is a vector that is kind of normalized. Sometimes in statistics, such approaches are called sphering. And here, by the way, this is also an element-wise division, right? So we're dividing the gradient vector by the square root of this thing. And the square root is an element-wise square root as well, right? So that's the idea. These are hyperparameters. Again, you see with every additional heuristic that we throw at things, we typically get more hyperparameters. This is usually not good, especially if the performance depends very much on what choice, and if that choice has to be changed for every problem, then it's not very useful in practice. But here, the good news is, it's already mentioned there, you know, this general learning rate, that needs tuning in practice. But this beta parameter that does this weighted aggregation here, this is typically 0.9, which means that at each iteration you take, you know, you do a weighted sum of the previous estimate and then 10% basically of the new one aggregated, 90% old one, 10% new one, if you will. And this epsilon parameter, why do we need epsilon here? Just to avoid division by 0, right? Whenever you divide by something, numerically you got to be careful. If that something gets 0, then the whole thing goes bonkers, right? And so typically for these, weightings, you would always, sometimes in papers they don't even mention this important. When you read a paper, sometimes when they divide by something, and you think about it, you say, what happens if that something becomes 0? In practice, what they often mean is divide by this plus epsilon. And that assures that, the thing doesn't get 0. But this is why epsilon is typically 10 to the minus 8, so it's just assuring that things don't get completely 0. And so this is called RMSprop, and you can see it's a little bit different. We don't aggregate the first, the momentum as in the gradients, as it was in the momentum, but we aggregate the variance, the squared gradients. These we aggregate over time, and then we divide by them to normalize the different components. This is called RMSprop. What's nice is you would say, wait a second, if we divide by something large, doesn't that make the updates even smaller? We want to move fast, and now you're dividing, by something, possibly a large number, then things get smaller, and then the learning will slow down. Well, you have to see it this way. If you normalize here, then all the gradients will have, will be better normalized, and then you can increase the learning rate alpha correspondingly. So, typically you would, once you introduce this variance normalization, then that would allow you to go to larger learning rates, because the oscillations in the y direction get smaller, and that means now you can do larger steps. So typically all these parameters have to be developed kind of together, right? Once you add this normalization, obviously you need to update the learning rate accordingly. So you suppress the outliers, you suppress, directions with very large alternating gradients. That's what you do here. You downweight them, and then you can increase the learning rate. And this is called the second momentum. The previous one is then often, it's either called momentum or it's called the first momentum. And when people ask you what is ADAM, ADAM is the solver that most people use nowadays to train neural networks. It's stochastic gradient descent with momentum, right? First and second momentum. And that's actually the idea of this ADAM solver, that you combine both. And so we're dividing by squared gradients, and the observation is, in this example, for example, in the y direction, this will be large, and so we suppress this, and in the x direction, this will be small. And as a result, we can then increase the learning rate. So this is RMSprop. It dampens oscillations for high variance directions, so directions where the gradient it keeps changing sign, and it allows us to take larger learning rates and thereby accelerate convergence. And that is what's called the second momentum. And the obvious question, I already pointed it out, can we combine both strategies, the first momentum and the second one? And of course we can, and this is done, and this is essentially what's in this technique called the ADAM. ADAM stands for adaptive momentum estimation. And so as you can see here, this is the first momentum aggregated, so the gradients themselves, they're exponentially weighted, aggregated into this m variable, the first momentum. And then we have the variance, v, that is aggregated, so the second momentum, as it's also called, it's aggregated here in this variable v, so the squared gradients. And then the update of this, integration would be that you take the m's and you normalize by these variances. First momentum, second momentum, so the mean of the gradients, or an aggregation of the gradients. And the second momentum is essentially the variance of the gradients, or some weighted aggregation of these. By the way, I didn't go too much into detail. It's not exactly the average of the gradients or the mean of the gradients over the iterations, but you see it's always this weighted sum of the previous one and the current one. And the result is that over time there is a slight dominance of the more recent gradient estimates. You can think about it, if you multiply this by 90%, then, at the second iteration, the momentum of the first iteration will be there by 90%. In the third iteration, it will be 90% times 90% times. So, and obviously, as a result, the initial momentum will be increasingly negligible the longer you move. So it's kind of a weighted average that gives more weight to the recent past and less weight to the historic old past. And that makes sense because, obviously you want to aggregate gradient information to identify oscillations, but if you move around in your loss landscape, you don't care about the gradients at time zero. At some point, they shouldn't matter to what you're looking at now, right? Because you are completely elsewhere in the gradient landscape. So you want to give more weight to the more recent gradient and variance estimates, and this is what's done here in this fashion. So this is an update that combines first and second momentum. So far, so good. But one of the issues is, and one should point out, this is not the update rule of Adam. Not exactly, but almost. Adam does one more thing, and this additional thing that Adam does is based on the question of what happens at the initial time. There is a bias in the sense that initially, there is no M0, and so you take, if beta 1 is 90%, then you only take 10% of the initial gradient rather than the full initial gradient. And the issue is you have to initialize somewhere, and if you initialize here with 0, you start with very small gradients, so the first steps will be very small. And what you can do is, and this is a bias in the sense, so if you initialize with M0 equals 0 and V0 equals 0, then the first estimates will be, not the full gradient at the initial time, but only, if beta 1 is 90.9, then this will be only 10% of what it should be. And what you can do is you can introduce an additional weighting, and this is what you see here. So you have additional weights, which are mk plus 1 over 1 minus beta k plus 1, and vk plus 1 over 1 minus beta 2k plus 1. And then you use not the vk's that you would get in the previous update, but the vk tilde and mk tilde in the updates here, right? That looks a little bit complicated. What is the consequence? Well, you can see it for yourself. When you set k equals 0, this normalization, you do 1, k equals 0 means at the first iteration you divide by 1 minus beta k. If you do that, it mainly just cancels this 1 minus beta. Oh, you don't see my pointer, sorry. I always think you see my pointer here. So you divide by 1 minus beta k plus 1 at time k equals 0. It's a division by 1 minus beta. That's exactly this 1 minus beta, right? Once you divide it, it means at the initial step you get the full gradient. That's what you want. At the beginning, you want to take a full gradient step. But when you let k go larger, keep in mind beta 1 is smaller than 1. With k going to infinity, ultimately this correction term will go to 0, right? Which means for larger k's, it will be exactly the weighted averaging that we had on the previous slide. So the first and second momentum combined. But initially, we have a correction that makes sure we take sufficiently large gradient steps. So it's a little bit just a reweighting such that you do larger steps initially, but with time, with k going towards infinity, these corrections will start to kind of vanish, right? Because then this beta 1 to the power of k plus 1 will go to 0, and this one will also go to 0. And so for k going to infinity, m tilde will be the same as m, and v tilde will be the same as v. So you have exactly just the weighted, so that the combination of first and second momentum. I hope that was clear. So the atom, you know, for very large k's, it is really this update that we have here, the black one. So that's the update. But for small k's, there is a bit of a correction that makes sure you take sufficiently large gradient steps at time 0. You would think, who cares about that? You know, just a few more steps, right? Well, you know, if you have millions of training data in each epoch, then every single step is very costly. So you want to make sure that every step is optimized. You know, some people would say, you know, if the first 100 iterations go in like a few seconds, why don't you just do 100 iterations before you do this, you know, bias correction, right? But we're talking about iterations and epochs that can take a long time. And then every step needs to be carefully chosen. And this is what you see here in Atom. They really went into this nitty-gritty details to make sure that every step is reasonable and meaningful. So this is Atom, exponentially decaying mean and variance of gradients that are aggregated in what's called first and second order momentum. And these, you know, and then you have the first momentum that drives things, and then you normalize by the second momentum to reduce the variance, this RMSprop idea. And then you have all these tuning parameters where the learning rate itself, this alpha we always call it, needs to be tuned. But the other parameters, beta 1, beta 2, they can, and this epsilon, they can usually be chosen like here, 0.9 or 0.999 and 10 to the minus 8, and then that tends to work. So these are also the default settings in PyTorch, for example. If you run this with PyTorch, that's the default settings you have in Atom. And so Atom is the default optimization technique that pretty much everyone in the deep learning community uses nowadays. I say pretty much everyone uses Atom, of course not, right? I mean, not everyone. This is especially in a research community that is big. There are always people trying different things, doing different things, and that's good. It should be that way because you want to explore, you want to come up with ideally better solutions than what others have done before. And this is always the ambition of all of us as researchers, to not just reproduce what others have done, but go beyond and see, is there better ways? And obviously there are many alternatives. There's the vanilla stochastic gradient descent. There's momentum, RMSprop, we talked about it. Then there's Atom. There's also a technique called AdaGrad. There's AdaDelta, AdaMax, NADA, AMSgrad, ProxProp. So there are many techniques out there that are often slightly different, sometimes just, you know, tiny differences, sometimes more significant deviations from what people usually do. Still to date, Atom is mostly the method of choice for training neural networks. But it's actually fun to play around with stochastic gradient descent and try different things to get a feeling for it. And it's easy, you get pretty immediate feedback. So here, for example, and this is important to realize, in this example, right, all the different solvers converge to the same solution for different times, right? You see that, you know, this is a comparison of different methods, and you see some are faster, some are slower. But one thing that's interesting is even though they end up at the same solution, they undergo very different trajectories to get there, right? And so with additional momentum, you actually do have a different solution path, even if maybe you end up at the same solution. And as we discussed, these problems are not convex. which means you have no guarantee that the different solvers will end up at the same solution. In fact, you could probably show that for two different solvers, there is always a problem where they will end up at different solutions, right? And here you see, for example, that stochastic gradient descent consistently goes down into the valley. Here, this is the red curve, right? But it's very slow. And some of the other methods that have momentum, first momentum, second momentum, etc., they go faster. But as a consequence, they tend to overshoot a little bit and run around in your solution landscape before they find the desired solution. And there may be cases where this momentum actually leads you in the wrong path, if you will. We saw that as well. And so the performance of the different solvers really depends on the particular loss function. And as a consequence, there is no one algorithm that is provably the best for all conceivable loss functions. If we had that, would be amazing, right? But this just doesn't exist. And so typically what you observe is that there is also a co-evolution of solvers and loss functions, in the sense that depending on what is the type of neural network architecture that we have, some algorithms may be better suited than others. More specifically, the atom might also be the ideal algorithm for the types of network architectures that we typically look at. Convolutional networks, ResNets, or transformers, or whatever. Here's another example. This is a nice, rather simplified example with 2 degrees of freedom, where in 1 degree of freedom, you start in an area where you have practically no gradient, right? So you're in the saddle point, and at that location, the gradient down the hill is very shallow. So in one direction it will converge, but in the other it goes very slow. And that is true especially for the plain vanilla gradient descent. So at the end of this video, it's still, the red point is still up there, right? Because it keeps oscillating in one direction and it doesn't actually move much in the other, because there is no normalization, there is no momentum, right? That it filters out oscillations and allows for larger steps, like you have with momentum. But even with a naive momentum, the green dot, it still gets stuck up there for a while. And so there is, various alternatives that, for this example, work much better. Here's another example, and this is an example that I like in particular because it's an example where you have 6 or 7 different solvers and they all go to different solutions, right? That can happen. So you train your neural network, and that means the set of weights that at the end of training you get out will depend on which solver you used. And that's not good, right? Think about it. It means, as an engineer, you're tuning your network architecture to do what it's supposed to do. Whether it actually does what you want it to do depends on the choice of network architecture, but it also depends on the algorithm you use to train it, right? And then if it doesn't work, is it because the architecture is wrong, or is it because your solver is not the right one? And that's not so easy. This is the usual big challenge for any non-convex optimization. If you're in convex land, then you can tweak your architectures, your loss landscapes in arbitrary ways, because provided you have convexity, you will find the optimum. And then if that's not good, the loss function is not right, because it's the global minimum of your loss. And if that's not what you want, then clearly the loss function doesn't capture your problem. Here, with neural networks and deep networks, it's different. The network may be the right one, but maybe your algorithm doesn't find the right parameter setting. Because maybe you used plain vanilla gradient descent, and maybe you should have used momentum, or maybe you should not have used momentum, right? So yeah. Some people say at that level, deep learning is a little bit of an art. Someone recently, a few years back said, deep learning is alchemy, and there was a huge social media fuss about whether it is or isn't alchemy. And people have reached out to me saying, Professor Cremers, do you agree that it's alchemy? I mean, it's a non-convex problem. That's what it is mathematically. Whether you want to call it alchemy or something else, I don't care. You shouldn't worry too much about what the world says. But it's interesting. So here, 3 different solutions, and depending on what algorithm you use, you find one or the other configuration. The good news, though, is even if there are different solutions that you end up finding, they might all be reasonable for what you want to do. So even if the weight, the vector of weights is not the same one, maybe the performance of the network on classifying the images is very similar, right? For example, if the loss is the same, then likely, at least on the training data, you should see a similar performance. Typically, the loss captures the performance on the training data in a way. So this is stochastic gradient descent. This is stochastic with momentum. This was the Adam solver. Maybe a bit more about optimization. Since we're talking about it now, this is a good moment to discuss this. Some notations here. We talked about so-called first-order gradient-based optimization predominantly. If you look at functions, here is a function f from R to R, then you can define a derivative, df by dx. You remember that from high school. Then if you have a function on Rm, so in m dimensions, this is what we typically have when we have loss functions in deep learning, right? We have a vector of weights, of unknowns, that we want to optimize, our parameters, and then we have a scalar loss. And then you have the generalization of the derivative to a function on m dimensions is called the gradient. It's a vector with components that are the partial derivatives of df by the different components x1 through xm if it's m dimensions. By the way, little notational aspect for those who have not much math background. For standard derivatives, you use the standard d. For the gradient, you have these so-called partial derivatives that use this round. It's called del f by del x1, etc. It's just a notational issue. It tells you that this function has more than that one variable, and it's the derivative with respect to just one of them. In addition, if you have something you might stumble over in the literature, in other contexts, you have something called the Jacobian, if you've ever seen that in the literature. It typically refers to functions that are vector valued. So they are defined on Rm and they map to Rn. And then the derivatives of first order derivatives, they form a matrix. An n by m matrix, and this is dfi by dxj, with I and j going through m and n. Right, so this is all the first derivatives of all the different components of f with respect to all the different variables that you have. The components of x. This is called the Jacobian. And lastly, a term that you should also have seen maybe is the Hessian. This is if you have a scalar valued function on Rm, then you can talk about the second derivatives, and these form a matrix that's called the Hessian matrix, based on a mathematician named Hesse, who, by the way, was a professor at TU Munich. In case you didn't know. I didn't know that until this year, actually. And this is quite great. We have very famous professors who've been here at TUM. And so this is the second derivatives. What are they good for? Well, one thing you can do with a second derivative is you can fit what is called a Taylor series. I hope you all know what a Taylor series is. If not, do look it up. It's one of the most amazing concepts in analysis. And the idea is that you can approximate any function, our loss, for example, as a polynomial in theta. So you start with what's called an expansion point, theta 0, And in the vicinity around theta 0, the function can be approximated with a Taylor series. This, for example, is a second-order Taylor series, which means I approximate it as a function, as a polynomial in theta up to second degree. This is the linear term, theta minus theta 0 times the gradient. And this is the so-called quadratic term, that is theta minus theta 0 transpose times the Hessian times theta minus theta 0. And this is basically a parabolic approximation of your function, if you will. Here, this is the first derivative, and this is the second derivative, the Hessian matrix that relates to what's called curvature of the function, right? So if you have a straight line, then the second derivative is 0, and then this is exactly the function. But if you have something that is not straight, but maybe more curved, then basically the way you can see this is you have your function, and then you can approximate it with the quadratic, which means you start at some value theta 0, you compute the derivative, you compute the second derivative that captures the curvature, and then you basically fit a parabola to your function. That's this. So the left-hand side, L of theta, is this, L of theta, if this is theta here. And the right-hand side, this is this approximation, right-hand side, if you will, of this approximation. This is this quadratic approximation of your function. And you can see the whole intent is to have a function that in the vicinity of your expansion point fits the function well. Fits well in the sense of it's identical at the expansion point in terms of all the derivatives, the first, the second, and how many others you want. If you don't know the Taylor expansion, look it up on Wikipedia. It's quite an amazing concept that drives a lot of science. A lot of physics revolves around Taylor series approximations of the world. Why do we do that? Well, because we can canonically not deal with high nonlinearities. And so we try to approximate things by a linear or a quadratic function. These can be handled better. And you can do optimization. What you can do now is you can say, I want to minimize my initial loss L. So what do? In each iteration, I fit a parabola, and then I step to the minimum of that parabola. And that would be my first iterate, so let's call it theta 1, would be the minimum of this parabola, theta 1. So that would be my next iterate, and then I fit another parabola here, and then I get theta 2, and you can see very quickly you converge to the minimum. This is an idea, it's super simple, it's something I remember thinking that should be how you do it, and indeed this is how people have done it, and it's not a new idea, and it goes back to the guy, you see the name, it's called Newton's method. So the idea is I take this approximation on the right hand side and I say find the value theta such that I'm at the optimum. Now you'd say, wait a second, I cannot find a closed form optimal solution for arbitrary loss functions. Right? And we talked about local minima, yes, but if you fit a quadratic paraboloid, that is by definition a convex function. And so there is a minimum, and you can solve that in closed form because it's quadratic. Minimizing a quadratic means you have a linear equation system. You invert the matrix. What matrix? The Hessian matrix that you have in here. The quadratic term has the Hessian matrix in it. And so if you take the derivative of this right-hand side and set it to 0, try this at home, and solve it, you will find the optimum is given by theta 0 minus H inverse times gradient of L. And if you paid attention, so this is the update step for the Newton method, it basically means I iteratively fit a parabola and step to the minimum of this parabola. This is very much like gradient descent. It's almost the same. Here's the gradient descent equation, stochastic or gradient, doesn't matter, right? The difference is rather than having a learning rate here, we have the inverse of the Hessian matrix. But otherwise, Newton method is practically identical with gradient descent. Right? But it's a big difference. Why? Because the Hessian is something I can compute. It doesn't mean I have an engineering parameter that I have to tune. No, the step size in the Newton, the pure Newton method, has no step size. It's given by the inverse Hessian, right? So the local curvature at every point tells you how far to go. And that makes sense, right? If you're in a landscape and you know it goes down this way, so I should be stepping this way, how far? Well, you look locally, how much does it curve? And that tells you where the minimum should be. And then you go there and try. So it's a very intuitive idea, very powerful, so powerful that you'd say, why don't we always use the Newton method instead of gradient descent? Anyone know why? Good point. Yeah. Yeah. So there are many reasons. You pointed some of them out. Indeed, some functions don't have a second derivative. We have nonlinearities. We have rectified linear units that are not differentiable. Computing second derivatives is even more. Assuming that the loss that you have is twice differentiable is a strong assumption. Next, you compute the Hessian in very high dimensions. It will almost never be convex. The problem, because you will have dimensions where things go downhill, right? You go to this point, and let's say, and then if you fit a parabola here, then this is what the parabola looks like. There is no minimum. So this Newton, analogy, it works well if you're in the basin of attraction, then yeah. And so that indicates what you might want to do in practice actually for complicated loss functions is a hybrid. Something that far away starts with gradient descent, like going down the hill, and once you get into this convex part, then you want to switch to a Newton method and go fast to the optimum. And this is often a method of choice, is some hybrid between gradient descent and Newton. Right. So you can see a little bit, all of these methods, they're not super complicated, right? These are ideas that you could have, if I had given you a day to think about how would you go about getting a minimum here, you would have come up with all these strategies at some point, right? So here is the Newton update step. Oh, by the way, one other issue why Newton methods are not super popular, let's say for deep networks. Keep in mind, we are estimating millions of unknowns, right? So your gradient vector is 1,000,000 dimensional. Now the Hessian matrix is 1,000,000 times 1,000,000. Yeah, that's really fun to compute and to invert, right? Exactly. Yeah, I'd forgotten that. Good point. Yeah. So for very high dimensional problems, the Newton method is tricky. Now we saw, we said stochastic gradient descent was the solution. We don't take all the gradients, we just take a subset of samples. Can we do stochastic Newton methods? Unfortunately, there isn't much on that, and it starts with the issue being that if you compute the gradient of a neural network and then you do it on a mini batch, you subsample and you then do the average gradient over the mini batch, and that gives you, we said, an unbiased estimate of the gradient. Unfortunately, if you compute the Hessian matrix on the mini batch, you get an estimate of the Hessian, but it's not an unbiased estimate, unfortunately. So somehow this is not as obvious to prove that you want some unbiased estimate there as well. And so this is all much more complicated. And people are looking into stochastic Newton methods, but I haven't seen much come out of it so far. So there's definitely need for more research from what I can see in this domain as well. So here's the update state of the Newton method. There is 1,000,000 parameters. The number of elements in the Hessian is 1,000,000 squared. The computational complexity of inversion of the matrix per each update step, I have to invert the Hessian. That's order of n cubed, where n is 1,000,000. yeah, you can see why people don't do Newton methods on deep networks. That said, you know, there's always hope that someone clever comes around and figures it out. Maybe one of you. Here's the gradient descent. In green, as you can see, it's and then the Newton method in red. So the Newton method has the effect of taking the curvature into account and often then finds a more direct route to the minimum. By the way, little question, if we do linear regression, we saw this is the classical linear regression problem. Can you apply Newton method to this problem, and what would you get? Does anyone see what you would get if we were to apply a Newton method to this problem? Yes? Exactly. We would get the solution at the first iteration because we approximate with a quadratic function. The loss function is already quadratic. So if we compute the second order Taylor approximation, we'll get the exact same function out. And the minimizer is exactly what the Newton method computes. So in one iteration, you're done. And this is the beauty. So it shows you a little bit, the closer your loss function is to something quadratic, the faster the Newton method will go. In fact, if it's perfectly quadratic, it's one step. And there's a lot of results that, you know, and there's, I should say, in the optimization community, there's two competing communities, the first order people and the second order people. First order is the people who do gradient descent and all sorts of variations of it. Second order people are doing Newton methods and variations of that. And they all have their arguments. The typical argument of, you know, if I put myself in the guy who does second order methods, he would say, well, we have a better convergence rate under certain assumptions. You can prove it converges much faster, and we don't need to determine a learning step size, etc. So it's more black box usable. You don't have to tweak it. You don't have to do any engineering. And then the second order method person would say it takes far less iterations to get to the optimum. And then the first order person would say, well, first of all, the Hessian is not computable and certainly not invertible for large problems, etc. So you can't do stochastic either. And, you know, sure, you have less iterations in the Newton method, maybe, but each iteration is massively more costly, typically, because you have to invert the Hessian matrix, right? And matrix inversion, when matrices get large, is not funny. It adds to your compute time. So even if you take 10 times less iterations to get to the minimum, but each iteration is 100 times more costly, you don't gain anything, you know. There is no benefit. And the whole discussion changes again once you take all the GPU discussions, right? Because with gradient descent, it's very easy to parallelize things on a GPU. Matrix inversion on a GPU, not so good, right? So Newton methods on a GPU, you have to think about how to do it. It's not as obvious. So, you know, there are many things to consider, and as a result, to date, it's still gradient descent in the neural network world, and it's still the atom solver by and large. I should say, though, there are all sorts of variants that make things more scalable. Right, so the Newton method issue was that it's cubic, the matrix inversion here. You can improve that. There is techniques like the BFGS method by Broyden, Fletcher, Goldfarb, Shano, and a variant called low-rank BFGS, LBFGS. So these are techniques that belong to a family that's called Quasi-Newton methods that are, you know, based on the Newton method. But what they do is they say, okay, the Hessian is not invertible because maybe it's not positive definite, or maybe it's too big or something. So then they compute approximations of the inverse Hessian and go with that. So rather than just taking step sizes like in gradient descent and tuning these, you take approximations of H inverse here, and there's different approximations. BFGS is an approximation that gives you, that you can compute in quadratic complexity. And this low rank BFGS, the LBFGS, is a limited memory approach that can do it in linear complexity. And so, you know, I'm saying things are tedious, but people have spent effort to make things scalable, to make things better. And so there are competitive alternatives that maybe one day someone will be able to make work for training neural networks. Oh, that's a good question. How much less accurate? You can't say in general. It depends on the application problem. But indeed, this is the trade-off often you get. You make things faster, but then they're less accurate. But in the end, you know, keep in mind that ideally, with time, these iterations should go to zero, right? And once they go to zero, it means the gradient is zero itself. And so then it means I'm at the optimum. So accuracy of the inverse Hessian approximations is an issue, but not super important, because by the end, once you converge, you're at the optimum. So that's kind of the same. And what approximations you do in between, you could say, who cares, right? But yeah, it's a good point. You know, there's things to consider. I wanted to mention one other algorithm. It's a technique that is actually inspired by second-order methods, and it is formally a second-order method, but it only computes first-order derivatives. And this is a method that's called the Gauss-Newton algorithm. And it, you know, here's the Newton update with the inverse Hessian. The problem is that the true second derivatives of the Hessian are often hard to obtain numerically. And so what you do is you approximate the Hessian by Jacobi matrix transpose times Jacobi matrix. Or, you know, if you have a scalar function, that would be the gradient vector squared, if you will. And then you do this inversion. And, you know, if you look at RMSprop, there's somewhat similar, right? There is a division by the gradient squared here. So there are connections between all these different techniques and methods. This is called the Gauss-Newton method. It is actually one of the most powerful numerical schemes for solving problems that are called nonlinear least squares problems. If you ever encounter these, the Gauss-Newton method and variants of it are the method of choice. And the idea here is that it's a technique where you have the Jacobians and only first-order derivatives of your loss. And then you can solve this system. This is another thing you do for very large problems, right? We have to solve this problem. Hessian matrix times update vector is the gradient. Sorry, Hessian matrix times the update times my update. Vector is, so theta minus theta 0, if you will, is the gradient of f. And you need to invert this matrix in the Newton step, but rather than inverting it, what you can do if it's too big, you just solve this linear equation system, and there are iterative solvers to do that. So when I said you don't want to invert million by million matrices, of course no one would do that, right? Obviously no one would, you know. So you would solve this equation system with iterative solvers. That means you don't explicitly invert the matrix, but you get an approximate solution after a certain number of iterations. And so this is what you can do. You can solve for this update vector here, x minus xk minus xk plus 1. And then what you can do, this is what I mentioned, is a hybrid between Newton and gradient descent. In Newton and gradient descent hybrid, what you do is you take not h, but you take h plus lambda times the identity matrix with a small parameter lambda. And for the Gauss-Newton approximation, you can do the same. This is called a damping in the literature. And it creates, because, why? Because if you just take very large lambda, you see, then this term will dominate. and then basically you have nothing but gradient descent. If this term here dominates, you can ignore the first term, and then you have xk minus xk plus 1 is the gradient, and that basically means xk plus 1 is xk minus the gradient. That's a gradient descent, what you have. For very large lambdas, this will be gradient descent, and for lambda going to 0, this will be this Gauss-Newton, or in general a Newton method. And so this is what you would call a damped Gauss-Newton method, and this is known as the Levenberg algorithm in the literature. 1944, I think, so pretty old stuff. It's called a Tikhonov regularization that you add, and it creates some hybrid between Gauss-Newton for small lambda and gradient descent for large lambda. And this is a damping factor, and I mentioned it, what you can do, and this is sometimes called a trust region method, because it basically means, yes, I want to do a Newton step based on this quadratic approximation, but I don't fully trust it. Right, so I take something like a gradient update, a little something in between, a gradient descent that says go a little step in direction of the minimizer, and the Newton method that says go to the minimum of the parabolic fit. And so this is why it's called trust region, because there is the parameter lambda that tells you how much do you trust the Newton update, if you will. So there's a region of trust that is defined by lambda, and you go basically as far as that allows you. There's a lot of trust region algorithms in the literature that have this property. And there is another variation, just so you've heard it. We don't actually use it for neural network learning, but in the literature it's called Levenberg-Marquardt. This is a technique we use a lot for our camera tracking in computer vision, etc. We use either Gauss-Newton or the Levenberg-Marquardt, which is almost the same, but rather than lambda times the identity matrix, you take lambda times J transpose J and the diagonal of this. So you have J transpose J, this is the approximation of the Hessian matrix, and then here you take the diagonal, so you have a matrix. It's not a unit matrix with lambdas on the diagonal like you have here, but it's lambda times whatever this matrix has on the diagonal. So it's a little bit more adaptive. This adaptation was introduced by a guy named Marquardt, who spent a lot of time looking at minimization algorithms, how they converge to the minimum, how fast, etc. And he found this often works better, especially for very anisotropic loss functions like the ones we discussed. And so it's, these ideas are, you can compare them to the ideas you have with in RMSprop, is very similar ideas that you do an adaptive weighting to make sure you don't take too large steps in one direction or larger in one and not too large in the other. Same idea. Right? Sometimes you would think, how did people come up with these techniques? When you look in the literature, it's always the same patterns of ideas that keep emerging. You see that the loss function is anisotropic, so you want to take larger steps in one direction and smaller in the other, and there is only so many ways to do that, right? So what does that mean? Where do we stand? What do we actually use to train neural networks? To come back to the topic of the class, you would typically use the Adam solver that has first and second momentum. You can also just consider stochastic gradient descent with the first momentum and leave out the second momentum. Depends on what you want to do. There are other techniques, but Newton methods, LBFGS, things like that. But for some reason, there are many reasons why these techniques have not been successfully used in training neural networks. But there's always hope. So a little bit more general on optimization. This is one slide that contains just a lot of names, right? So I'm not sure this is very useful. I adopted this slide set from previous classes. you know, every word would need more time to go into, but just so you've heard some of these approaches. For example, if you want to solve linear problems, linear equation solvers, there's LU decompositions, QR, and Cholesky decompositions of matrices that can be applied to make solutions faster. I'm sure in high school you learned Gaussian elimination. That's one technique, but there is a lot more. There's iterative solvers called Jacobian and Gauss-Seidel, very similar, you know, very subtle differences there. Then there's conjugate gradient and so-called precondition conjugate gradient methods that are also iterative solvers to solve big linear systems. And these are being used very frequently every day for various problems. Once your problem is nonlinear, so you don't have a linear system, then the default method of choice is gradient descent, a first order method, provided the loss function is differentiable. And if it's big, you can go to what's called stochastic gradient descent. We discussed that. For you know, if it's sufficiently differentiable and not too big, you can also revert to second order methods, Newton methods, Gauss-Newton, and these is BFGS or LBFGS methods, or the Levenberg-Marquardt algorithm. There are lots of other algorithms that people have deployed for various settings. For example, if your problem has a discrete nature, and then you can revert to genetic algorithms, MCMC sampling methods, Metropolis-Hastings sampling, graph cut methods also for graph represented loss functions. There's also techniques for problems that are not differentiable, right? We always said we need gradients for gradient descent. What if your problem is not differentiable? And that can happen in a way, even, you know, even the ReLU is not differentiable, right? And people were saying, well, what do we do here? There are different ways to deal with that. Often you can approximate these gradients, you can approximate them with something smooth, but there are explicit techniques for non-smooth problems that use Lagrange multipliers. For example, if you have constrained optimization problems, there are very powerful ADMM and primal dual proximal. This is something I worked on for years, these different algorithms, iterative solvers for non-smooth problems. And I do have some hope that these techniques could one day replace the atom solver in training neural networks. And I think there is a significant need for better algorithms because we live in an age where sometimes training a network can take days and weeks. So anything that accelerates this will be very appreciated. And it's not just time, but time scales and is related to energy consumption, right? You don't want to train something like ChatGPT and burn as much energy for training this model as an entire country consumes. But this is where we are standing pretty soon, right? So the needs of machine learning, the energy needs of machine learning algorithms are massive, and it all ultimately comes back to finding smarter algorithms that need fewer iterations, that go faster. And, you know, since I know there are, you know, the class is a bit diverse, people have different backgrounds, but I recently found out there are some people who have a math background. Who is a student of math here? Oh, quite a number. Interesting. So here's for the more mathematically inclined. I thought I would add a section that wasn't in the initial slide deck. And this is an algorithm we published in 2018. It shows you an alternative way to train a neural network, and it indicates that there is potential and that there is hope that one day we'll come up with something better. And it's a technique that we call proximal backpropagation. So here's the loss function. You should, you know, it's not written as a graph, but here's the graph, right? So we have a set of weights at each layer, and then we have a weighting of the neurons to each layer, and then we have this nonlinearity sigma, either sigmoidal or ReLU or whatever you want, right? That's the original loss function. This is the weights I care about. Now what we can do is we can introduce auxiliary variables to and formulate what's called a constraint, an equivalent constraint optimization problem. And here it is. So basically, I just take the loss at the last layer, this Ly, and then theta L1 is the weights in the last layer, and AL minus 2 is the output of the previous layer, right? And that's the loss I care about, and these are my unknowns. And now I have constraints for every layer, so I have as many constraints as I have layers, and for every layer I say, first of all, the output of the linearity, this is this function phi of theta L AL minus 1, is just multiplying the neurons of the previous layer with the respective weights. So this is, and then adding a bias, if you will, right? So this is this function phi, it's just a linear transformation of the output of the previous layer with my unknown weights and biases. And that should be the input to the nonlinearity, ZL. And then this ZL gets piped through a nonlinearity, and that gives me the output of that layer, right? And so I have one constraint to say this is the linear transformation. So the output of the linear transformation is stored in the variable ZL, and the output of the subsequent nonlinearity is stored in the variable AL. So we add auxiliary variables. This is a common technique when you do optimization, is you increase the number of unknowns. You'd say, why would you already have millions of unknowns, why would you add more? Well, the aim is to make the loss function simpler, because each of these constraints is extremely simple. How do you minimize a constrained optimization problem? Well, one way to do it, and this is this is the linear transformation, and this is the output of layer L that we store in this variable AL with the nonlinearity sigma. How do we enforce these constraints? So this is the optimization problem. We propose in this paper what's called the quadratic decoupling strategy. It's a common strategy where we basically have three terms in the loss function. One is our original loss, the loss on the last layer. And then we have a set of terms, each of them enforcing this constraint and that constraint, right? It's very easy. That's why it's called quadratic decoupling, because the constraints are enforced by quadratic losses, right? We say, the linear transformation of the previous layer should be the same as ZL, and we penalize the discrepancy with a quadratic penalty, and this is weighted by gamma, so we have these weights, and so these two constraints are basically taken care of by these two terms, right? Same here, this says the output piped through the nonlinearity should be the input for the next layer. And then we have weights gamma and rho, and now you can basically see that if I increase gamma and rho, then it couples the things such that ultimately these two constraints are fulfilled. But this is then the problem I optimize, and we can do that by alternatingly computing gradient descent steps and what's called proximal steps. I don't want to go too much into technicalities, but proximal steps is a generalization of gradient steps for non-smooth optimization problems. There is a lot of literature on that. People like Nesterov have worked on proximal methods as well. What's the benefit of doing this? Well, we can look at convergence, right? That's what we care about. Here's the first experiment we did with this, and we compared. Here's the backprop in blue, and here's our Proxprop algorithms with different parameterization. There is an inner loop where we do conjugate gradients, and if you take 3, 5, or 10 iterations, or the exact, you get different speeds of convergence. And what's clear to observe, as a function of the number of epochs, our approach is much faster than backpropagation. right? You can see it. Also note it's much smoother, right? The backprop loss, it kind of oscillates down the hill. It's not pretty, if I should say. And our curves are much smoother, right? It's because of this decoupling. It kind of separates the different issues that the thing should do, softly coupled with quadratic constraints. It makes things a little bit more manageable somehow for the algorithm. That's very encouraging, but it's as a function of epochs. So iteration numbers, if you will, right? It's not as a function of runtime. Here's the plot if we plot it in hard currency, seconds, minutes, whatever, right? And then you see things look different. Then all of a sudden, this jaggedy backprop, is pretty much on par with our Proxprop in purple here, right? So we get something that is same performance as backprop, but is smoother at least. I would say that is an advantage if you have something that decays smoothly as opposed to something that is jaggedy like that. This is on an MLP multilayer perceptron, Cypher 10. Then we looked into convolutional networks. This is what people care about more. And the reviewer said, really nice on MLP, wonderful, but we don't care about MLPs. People care about convolutional networks, about ResNets, about other networks. Can you show how it works there? So we did, and we found we have something similar. Here's the backprop in blue. Here's the proxprop in red. So as the function of epochs, it's faster. But unfortunately, in terms of time, it is no longer faster. And this is always, finding an algorithm that really works on all conceivable architectures and outperforms what people have done is not easy. Again, here's the comparison, epochs, time. The issue when you convert epochs into time is that is something that is highly dependent on the compute architecture you have at hand, right? So this can change with more sophisticated architectures. For example, GPUs are notoriously good to run things in parallel, but once you need CPU compute, for example, to invert something, like in the Hessian matrix inversion something, then things get really slow. As soon as you need to communicate between GPU and CPU, that kills all the runtime advantages of the GPU, or much. So the transition from epochs to time is something that was like that 2018 with more advanced hardware. This may actually change, and then maybe we can reproduce similar curves as a function of runtime. I don't know. Here's another interesting observation. We looked at the validation accuracy, right? We train our network, we minimize the training loss, and then we test it. What we found, you see it here, during training, the network, it generalizes better, right? The blue curve is the backprop. It's actually Adam here with the backprop. And what we use is the same momentum, weighting, etc. Obviously, these heuristics, you want to include them because they accelerate things. And so we have Proxprop with first and second momentum and this bias correction. And you can see it generalizes better so that the validation accuracy is higher. This is, I would say, promising. So to summarize, and this is, I should say, 6 years old, this paper, right? The conclusion of this, study and this algorithm that we developed is it takes less epochs to converge to a good solution. It shows a smoother convergence curves. So they're less jaggedy, less oscillatory. It shows a higher validation accuracy on the convolutional networks, but the runtime is not better. And in the end, that was the deal breaker. That was where the community said, we're not going to replace Adam by your method because in terms of clock time, it doesn't provide an improvement. So that's where we stood in 2018, and we couldn't see how to go beyond this, but maybe some of you are interested. If you have a math background, if you're interested in optimization, I think there is a lot of potential here to go beyond Adam. Why is what? Why are the convergence plots smoother? I mean, in the end, these are the experiments that show this. Oh, why is smoother preferred? That's a good question. I would always say smooth is better because, I'm proposing an algorithm that is apparently minimizing the loss, right? But if it goes up like that, it means there are steps where the loss doesn't decrease, it increases. So there's something the algorithm does that's not right, right? At every step, supposedly, gradient descent should reduce the energy. If it keeps going up every now and then, it means there are steps in there that are fishy, that are not what they're supposed to be, right? Mm-hmm.
As you do the backpropagation, each of these layers has to do their own step of gradient descent or
Mm-hmm.
right?
Mm-hmm.
So so basically, if you have, for example, 100 affine layers, you need to do 100 gradient descent steps separately from each other.
Yeah. Yeah. Yeah, so short summary, people use Adam. We tried to do better than Adam. We managed partly, but not fully, right? And so it's a little bit inconclusive at the end. And one reason why people have not adopted Proxprop is even if you are on par, you have to get into the big software libraries that everyone uses. And it's easy to get in if you have a massive advantage. If you can say, I am 30% faster in terms of clock time on all the established architectures, then you have a story. And then you can go in and then they will adopt your method over the Adam method. But if you show something that is sometimes better, sometimes worse, and on average the runtimes are similar, they're going to say all these auxiliary variables that obviously are likely going to add to the memory footprint of your method, what's the benefit? There's no clear benefit, right? There's a question there. So the question is, what does CG mean? It goes into how exactly we solve these different updates on the auxiliary variables. And there is an outer loop and an inner loop. And the question is how precisely we solve the inner loop, how many iterations of whatever solver, in this case, conjugate gradients you dedicate. Do you do 3 inner iterations per outer or 6 or 9 or whatever? And we see that depending on how we do it, sometimes one or the other is better. And that's why we plot all of this, because if there was one preferred strategy, we would just say that's how you do it and be done with it, but it indicates that it's not as clear, right? All right, so that summarizes this part of the lecture. It says next week, this week, next week. I'm going to move on. Here's more literature also. You have it in your slides, though, so you can revert to that. And that brings me then to the next part of the lecture. And that is training neural networks. So the last part was a little bit mathematical about optimization, about stochastic gradient descent and momentum, etc. Right? So we talked about how to set up networks. We talked about the gradients that you can define with the indices. By the way, again, keep in mind these 3 indices that we typically have. L is the index of the layer, M is the neuron in each layer, and N is the input for each neuron. There's N different possible inputs, right? And then these are the parameters, the weights in each layer, and the biases that we can compute the gradients for. And that is a long vector of gradients. We saw how we can compute this with backpropagation, numerically going layer by layer through these compute graphs to determine these derivatives. And then we saw we can update them with gradient descent, or in practice more with a stochastic form of gradient descent, where we have mini batches and we average the loss over the mini batch and the gradient over the mini batch. And so this was the idea. Then we saw we can add momentum, either the regular momentum or this more sophisticated momentum by Nesterov. We also saw that there is this RMSprop that computes the second momentum, or the variance of the gradients, that is aggregated in this exponential weighting. And then you can have an update step that includes both either just the second momentum in the RMSprop, or we saw that the atom combines the second and the first momentum, and it also does this bias correction by these factors that has the little effect to make sure that at the first iterations we actually take sufficiently large steps. So this is atom. I also mentioned alternatives that are out there, but as I said today, people mostly use atom for training neural networks. And what we're going to talk about in this part is now less about the theory of solving it, but more about how you actually implement things with the tools that are at hand. So a little bit more about learning rates, the implications, right? We said you want to find a good learning rate. How do you pick the learning rate? This is a big challenge. We saw all sorts of weightings, momentum, but the learning rate remains a parameter that you have to tweak. Ideally, over the course of epochs, you want to reduce the loss, right? And you can see, and this is what I highly recommend, whenever you optimize a neural network, develop the tools, or take the tools, make use of the tools that allow you to visualize progress. How do you visualize progress? You can plot convergence functions, where you plot the loss over iterations, over epochs, over runtime, however you want, right? This shows you, does your method work? And there are different ways you can read these plots. They help you visualize, because we're talking about millions of dimensions. You can't look at the loss landscape directly. We cannot visualize a loss in millions of dimensions or thousands of dimensions, right? But you can visualize the loss evolution, because that's a scalar function as a function of time or epoch. And you see that if the learning rate is very high, then the loss doesn't actually go down, because you oscillate and you have maybe a parabolic loss, but then you bounce around and the loss just keeps going and diverges completely. So the loss goes up, but also the solution itself will oscillate randomly. And that indicates possibly is your learning rate too high. If you have a high learning rate, you will often see the green curve that makes a quick descent on the loss, but then somehow it doesn't move much anymore. The loss doesn't keep going down, it levels out, it flattens out, and that could be because you're near the minimum, but you're bouncing around the minimum, right? And when the learning rate is too low, then you get a decrease in the loss, but it's very linear, as you can see. That's typically not the kinds of curves we want to see. If the loss reduces at every time for about the same amount, then this indicates that maybe you can go with a faster learning rate, a higher learning rate. And so ideally the curves that we want to have are curves like the red one, where the loss kind of decreases fairly fast and things keep going down. And so this is the kind of behaviors you observe and you can monitor, and that will give you indications of how to choose your learning rates. And as I said, one issue with a high learning rate is you will take steps towards the minimum, But then at the minimum, you don't want to oscillate over, right? Because then it just bounces back and forth around the minimum. So what this indicates is possibly you need a high learning rate when far away and a lower learning rate when you get near the optimum. And you remember this paper from 51 about stochastic gradient descent. They actually advocated a specific learning rate that had this B property, that it was a learning rate which was 1 over n basically, and n was the number of iterations. So you do 1, 1/2, 1/3, 1/4, right? And that's roughly what this kind of plots will indicate. And so there's different strategies to pick learning rates, to do adaptive learning rates, or to change the learning rate over time. So different recipes, right? Like the paper of Robinson Monroe, 1951. This was 1 over n, and this is what we have here, right? More or less, this is 1 over 1 plus decay rate times epoch, right? So if the decay rate is, doesn't matter, but you see essentially as a function of epoch up to this 1 plus, it's 1 over epoch, right? So we have at epoch 0 we'll have 0.1, then we'll have 0.05, 0.033, etc. And so the learning rate will gradually decay if it's like a decay. This is called the decay rate. And this is something that's been shown to work fairly well, but there are other options. This is a linear decay rate that also can work. Basically, you start with an initial alpha, and then at each iteration you take away a certain percentage, right? Let's say if t is 0.1 or 0.5, for example, then you take, you reduce the learning rate by half every time. Also an option. Or an exponential decay, so alpha is t to the epoch times alpha 0, so you have at epoch 0 you have alpha 0, and then you have an exponential decay of this. And obviously t should be smaller than 1, otherwise this doesn't make sense. T is called, and you can have this is then the decay rate. So there's lots of different ways to define iterative schemes to define your learning rate. There's lots of strategies people cooked up with, but in practice you can't really say there's one that fits all, right? So sometimes it's a matter of trying different schedules for the learning rate. And it's tricky because you need to manually specify the learning rate for the entire training process. You need to define the schedule by how the learning rate is reduced in each iteration. Manually set the rate for every n epochs. And the question is, how do you do that? Trial and error, that's like really tedious. And to some extent, if you have some experience, and what helps is looking at the loss curves. And that, as I said, indicates whether your learning rate scheme is too small or too large or whatever. And you can do that. You can consider the number of epochs that it takes, the training set size, the network size. They all play a role as to what loss reduction do you expect. And it's really weird because this shows you that when it comes to tweaking the learning rate, it becomes very hand-wavy, right, all of a sudden. And if you remember, the whole aim of the deep learning development was to say, initially we had hand-designed filters to filter images and detect objects. Now we took away all this hand design and we come up with a principled method, a learning-based method. But once we train it, it's very much hand design again. And this is partially related to this gradient descent being the method of choice here. But there are some basic recipes for training. You're given a data set with ground truth labels, xi, yi is the label for each input training sample xi. Typically, the number of dimensions in x is much higher than the number of labels. So you would typically have millions of images and maybe, let's say, 100 classes of objects, right? It doesn't make sense to consider 1,000,000 classes if you only have 100 training samples, right? Then clearly most classes are not in the training data, right? So obviously you want this regime. And in practice, so then you take a network, and I is often in the 100,000s or millions, so the number of training samples that you have. Images, for example. Then you take a network, you have parameters, the weights and biases, and then you do stochastic gradient descent or some variation to find optimal parameters W and B, and you use the gradients from backpropagation learning. This is how you do it. So you have a million labeled images, let's say, and then a set of, let's say, 500,000 parameters in your network. So the gradient has 500,000 dimensions. You have n is a million. So you can see things get expensive to compute, right? Computing gradients with respect to 500,000 unknowns and on a million of samples, it's costly. And then, this isn't, the real learning happens in practice when you show generalization to an unknown data set. And this is the challenge. Ultimately, we want to train on images of cats and dogs, and we want this network to be able to label cats that we've never seen before. And this is the challenge, but the question is, how do you get to that challenge, right? How do you get closer? And so often you have to start small. This is a general recommendation in any area of science, that you start small. And the hope is that based on the train set and the optimized parameters, that we have a network that does generalize and that does classify new images, unseen cats and dogs. I mentioned the split that you do in training set and validation set and test set, and I mention it here again. The test set is really only for the final performance validation. You don't use this for training your parameters, because that would mean you're overfitting. That would mean you use the knowledge about what you want for computing your weights, right? That would be cheating, right? This is very important to understand, that the test set should never be touched, only at the very end. But the validation set is there, and the validation set serves for, optimizing hyperparameters. The biggest hyperparameter being the learning rate, right? So you can look at the validation error to tell you whether your learning rate is suitable or whether you should need to adapt it. So in practice, there's different splits you can do: 60, 20, 20, or 80, 10, 10. And during training, the training error comes from averaging the mini-batch errors. So this can be done during training, but then you can also compute the validation error. That typically you only do every n iterations. So you do iterations on the weights, and every n iterations you would, compute a validation error on the validation set. In practice, you would obviously, to compute the validation error, you would, not use the entire validation set, but maybe only a certain fraction of it. Much like mini batching in the training, you can do the same to compute the validation error, to estimate it. You don't have to have the exact error, so you take a random subset, to get the validation error. And the nice thing about the validation error, this is fairly fast to compute, because you only need a forward pass in your network. You don't need to compute gradients, so you don't need to do backpropagation to compute the validation error. So this is typically fast, especially once you have things running on a GPU. And so as a result, since the validation error is just a forward pass and that can be done fast, you do have an interest of frequently validating. And why? In order to get quickly an idea about, are my parameters properly set? Is my learning rate the right learning rate? And there's nothing worse than, training a neural network for several days, black box, set a learning rate. Sometimes beginners do that. And then they run it until convergence. And then they find, oh, the learning rate wasn't well chosen, right? So you just wasted 2 days of training. And if you can determine quickly that the learning rate is not suitable, you should adapt it quickly. So once you do frequent validations, you can determine whether your learning rate is appropriate and the hyperparameters are appropriate, etc. So don't train for days to realize that you had the wrong learning rate. One last thing here, split in train and test. You can do this so-called cross-validation. This brings in even more randomization. So if this is your entire data, you would split into, this being validation and this being the training data. So if this is the train and validation data, in the second run you might use this mini batch for validation and the rest for training, and so on, right? So that way you get a little bit more of randomness into the picture, what you train on, what you validate on, right? So that you don't get a bias. If you have really weird cats in your validation set, then you would always get a bad validation error, but by stochastically sampling what data I take as validation set, you will be less prone to that issue, right? Because if you have a certain size training data and validation data, it might happen that all the weird examples end up in the validation set for some randomness, right? And you want to be a little bit more robust, and so you would split things, differently. And this becomes very important when you have little training data. That means pretty much always. Because in the deep learning age, you always struggle with not having enough training data. You'd say, wait, we have 1 million data. Yeah, but if your model has 1 million parameters, then 1 million training samples isn't all that much. And the whole challenge is we want to go to big models that have powerful capacities, and that means we want a large set of unknown parameters, and in order to estimate them reliably, we need a lot of training data. And then if you work on medical, and every time you need a ground truth label, you need to ask the medical expert. You can imagine they have very high salaries, these medical experts, the radiologists, etc. Right? You pay them per sample, right? And then, training data can get very costly, and we just had a symposium yesterday on generative AI, and people were saying the biggest challenge is not the algorithms, not the GPUs, it's getting the training data. And for legal reasons, owning the training data. There's big companies who somehow overlook that aspect. All right, I don't want to name names, and that's it for today. I'll see you next week.